This video is going to give us a couple of ways to analyze graphs other than just by looking at them. The first of which is called the adjacency matrix. So let me give you a quick little graph here. Let's say A, B, C, and D. And let's put some random connections here. And I'll leave it like that. So the idea of an adjacency matrix is you're going to create a matrix and you first ask yourselves, how many vertices do I have? Well, there's 4 vertices, and so that means that it's going to be a 4x4 matrix. And what you're going to do is every place where things are connected, you're going to put a 1, and where things are not connected, you're going to put a 0. So you imagine that you have A, B, C, D along the top and A, B, C, D along the side. And you say A is connected to B, yes, that gets a 1. A is connected to C, yes, that gets a 1. A is connected to D, gets a 1. A is not directly connected to A, so that would be my first row. Then I say B is connected to A, B is not connected to B, B is not connected to C, and B is connected to D. Great. Similarly, C is connected to both A and D, but not to B or itself. And D is connected to B and C, but not to itself. So this is an adjacency matrix. Now I do want to point out that there is not just a single adjacency matrix for a given graph, and the reason why is we like A, B, C, D in that order. That's what we're used to in life, but there's no real reason why you have to put them in order A, B, C, D. You could have done D, A, C, B. And so by choosing a different order, you're going to get a slightly different matrix. So D is connected to both B and C. It's going to be that. And A is connected to B and C. So A is going to be like, and D, sorry. And C is connected to A and D. And B is connected to A and D. And so you see here, you do get a different matrix. However, these two matrices contain the same information. They contain the entirety of that graph and how things are connected. Now, I do want to point out that there are variations on this adjacency matrix. For example, if you had a graph with a loop, then you could, sorry, I don't want to make that arrow there, just a regular loop. If you have a loop there, then A would be connected to A. You can have a 1 there, and that'd be fine. You can also have directed graphs. Let's say A goes to B, but not vice versa. Then A would go to B, but B would not go to A. Right? So if you only have a one direction there, A would go to B, but B would not go to A. So you can have adjacency matrices for directed graphs. You can even also have ones for graphs that have multiple connections, similar to the bridges of Königsberg example that we had there. So in this particular one, again, if I do my A, B, C, D ordering, then I would say A is connected to B twice, A is connected to C not at all, and A is connected to D once. Similarly, B is connected to A twice, B is connected to C twice, and to D once. C's got 2 onto B and 1 onto D, and D's got 1 onto A, B, and C. And so you can have numbers other than 1 there when you have more than one edge connecting the same vertices. Okay. the fun thing you can do is if you call this matrix, say, a letter, let's call it, I don't know, I already used A, so I'm going to call this X here. It turns out if you were to, say, take this matrix and square it, which you can do by hand in your calculator, then you would get a new 4x4 matrix. And the thing is whatever number is in here, that's going to be the number of ways, and let me put my reference here, A, B, C, D. That would be the number of ways you can go from A to B in 2 steps. And if you had done x to the 5th power, then the matrix elements would tell you how many ways to go there in 5 steps. So that's a really interesting property that we use in some problems. There's something called a random walk, which it's possible you've heard of. It's also possible you haven't heard of. The idea is if someone is randomly flipping a coin and deciding where to walk on the ground, and you want to say, well, how many ways can he get back to his starting point? You could do something like a matrix power there, and you can see, well, in 5 steps, there are 17 ways to get there. So, like I said, it's a pretty interesting property of the adjacency matrix, and this is one way we can study a graph through matrices and numbers rather than looking at a picture. There's another type of matrix called an incidence matrix. And I'm going to go ahead and use the Bridges-Koenigsberg example again here. But what's going to happen is you base it off of the edges, not off of the vertices. So I'm going to number these. I'm going to call this edge 1, 2, 3, 4, 5, 6, and 7. And you can do this either with rows or columns here. I'm going to do it with rows. So I'm going to have a 7x4 matrix. And what this is going to be is each row is going to correspond to one of your edges. Just going to need a little more room here. And then across the top, I'm going to write down the vertices, and then what's going to happen is edge 1 connects A and B, so those would get a 1 there and then 2 zeros. Edge 2 also connects A and B. Edge 3 connects B and C. Edge 4 connects B and C. Edge 5 would connect A and D. Edge 6 connects B and D, and edge 7 connects C and D. So an incidence matrix is talking about listing the edges and indicating how they are connected. If you have a graph with a lot of edges, this could take a really long time to write it out. On the other hand, if you have a graph with a lot of vertices but not a lot of edges, then the adjacency matrix might be a waste of time with all the zeros there. Also, the incidence matrix is something that you could easily say has an input to a computer program for someone to enter a graph by just saying enter the incidence matrix. So regardless, it just depends on the problem which is more useful. I want you to know both of these concepts here. I might ask you for one or the other, or I might give you one of these matrices and say draw the graph associated with that. So you should know how to handle these here. And the last concept on this video is the idea of isomorphism. Now I'll give you the official definition here. Two graphs are isomorphic if and only if there is a one-to-one onto, and when you have both of those, we also call it bijective, function between the vertices of the two graphs that preserves all the edges. Now let me give you a quick example here. What if I had a graph that had the 4 vertices A, B, C, D and connections this way, and maybe I'll add one more connection across B and C there. And then what if I had a graph where I called them X, Y, Z, W, and I connected them all around the outside and connect Y and Z there. And even though those two graphs are not the exact same, their vertices have different labels, so they're not the exact same graph. In some sense, they basically are the same graph. There's really no difference between them. And so we would call these graphs isomorphic, meaning that they're basically the same thing, even though they're not perfectly the same thing. And this is a concept that's used quite often in mathematics. The way that it was first explained to me is something that I've always remembered here, is that if you were to count in, let's say, English, 1, 2, 3, 4, or in Spanish, or in French, or in German, whatever your favorite language is, eins, zwei, drei, vier, or uno, dos, tres, cuatro, the idea is that regardless of the words you're using, you're still meaning the same thing. And that's the idea of isomorphic. So these two graphs, even though they look slightly different, they really mean the same thing. And one way to tell if graphs are isomorphic is if you can find adjacency matrices or incidence matrices for the two graphs that are the exact same, then you'll know they're isomorphic. I do want to warn you, though, that as we saw up here, there is not just one single adjacency matrix for a given graph, and that means that if you don't order things right, your two adjacency matrices won't look the same and you might not be sure they're isomorphic. In fact, it's very difficult for big graphs to prove that they are in fact isomorphic. On the other hand, it's pretty easy to show things are not isomorphic a lot of the time, because isomorphism preserves things like the number of vertices, the number of edges, the degrees of vertices, and so on. There's other things as well. And so if you look at your graph and one of them has 5 edges, one of them has 2 edges, you know they're not isomorphic. You don't do any more work than that. If you have one that has 3 vertices and one that has 17 vertices, guess what? Not isomorphic. If you have one graph that has one node that has a degree of 7, and on the other graph there's nothing degree of 7, you're guaranteed they're not isomorphic. It's just showing that they are isomorphic. That's the hard part here. And so you can look at several examples on your homework and you can see if you can figure out whether they're isomorphic or not.